Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
We talk a lot on this deep dive about stars dying, which, sounds inherently dramatic.
It does.
But the universe doesn't really do simple melodrama. It deals in complexity and just unimaginable violence.
Exactly.
And we're not just talking about a star dying here. We're talking about a whole category of cosmic events that we may have been fundamentally misclassifying for decades.
Or maybe a better way to put it is that the cosmos has just introduced a new hybrid category of extreme violence.
A new category entirely.
Yeah. We dove into a deep stack of sources all about this one cosmic event, officially called AT 2025 Hodgers. And this event, frankly, it acted like two different things at once.
A massive star explosion and a dead star merger.
At the same time, it's presented astronomers with this really compelling paradox. It fundamentally challenges our rulebook for how stars are supposed to die.
So our mission today is to unpack that.
It is. We're going to synthesize all this confusing, contradictory data, the gravitational waves on one hand and the light waves on the other, to understand the leading hypothesis, the birth of a brand new, first-of-its-kind phenomenon called a superkilonova.
I find it endlessly fascinating when the universe just throws out a plot twist, something that forces us to rewrite the physics textbooks.
It happens more often than you'd think.
But before we get there, we really need to quickly contextualize these cosmic blasts for you, because understanding the established difference, the difference between the two main types of explosion, is just crucial to grasping why AT 2025 fulls cause such an astronomical identity crisis.
That's absolutely the right place to start. Think of it like this. Stellar evolution has two massive endpoints, and each one is responsible for seeding the universe with the basic chemistry that makes up, everything, including us.
The first, and probably the one people have heard of, is the supernova.
Yes. This is the death of the behemoths. When the most massive stars, the ones far bigger than our sun, burn through their fuel, they collapse violently, and then they explode.
And that explosion seeds the universe with what exactly?
Lighter heavy elements. So things like carbon, oxygen, nitrogen, all the way up the periodic table to iron. These are the elements that form the bulk of planets and life. They're essential, but they're kind of the common currency of stellar explosions.
Yeah.
It's a stellar collapse event.
Okay, so if supernovae are the common currency, kilonovae, they're the mint. This is where the universe forges the really rare and fancy stuff.
That's a great way to put it. Precisely. Kilonovae are fundamentally different. They aren't star deaths, they're dead star mergers.
So not a collapse, a collision.
A collision. It happens when two ultra-dense deceased stars, usually neutron stars, spiral into each other and just smash together at incredible speeds. And this is the only known environment in the universe where you get the right combination of insane heat, density, and a massive continuous flood of free neutrons.
Which allows for something called our process.
The rapid neutron capture process, or R process.
Yep. And why is that process so important for us, here on Earth?
Because the R process is how the truly heaviest elements get forged. We're talking gold, platinum, uranium.
The good stuff.
All the precious metals, the radioactive components that are fundamental building blocks of planets. They are incredibly rare, born from these highly violent events, and they're just astronomically significant. So when you find these elements here on Earth, that gold in your ring, it's the shrapnel from a kilonova that happened a long, long time ago.
The physics of the explosion dictates the chemistry of the universe.
That's it.
So to really appreciate just how strange AT 2025 Fellatese was, we have to start with the baseline, the universally accepted gold standard kilonova.
Which brings us to the blueprint of stellar collisions, Kilonova 101.
And there's one event that really stands out.
The benchmark event, absolutely. The one that proved the theory of kilonovae was GW170817. That was back in August 2017.
Before that, the idea was purely theoretical.
Purely theoretical. The idea of two neutron stars merging and forging gold was just a model. This event was historic because it was the first, and until our new friend, AT 2025 launchers, the only time we had an unambiguously confirmed detection. It included both gravitational waves and light waves.
That dual detection, Seeing the ripples in space-time and then the flash of light?
It changed astronomy forever.
Okay, can we zero in on the gravitational wave part for a second? What exactly did those ripples in space-time tell us about the objects before any telescopes even looked up?
Right, so that's the real power of LIGO and Virgo.
Yeah.
The detectors, they pick up this minute stretching and squeezing of space-time. It's caused by the incredible acceleration of these neutron stars as they spiral into each other.
The chirp signal.
That's the one. And by analyzing the frequency and the amplitude of those incoming ripples, we can mathematically model the mass, the spin, even how far away the objects are.
And for GW17U817, what did that chirp say?
The signal was clean. It was beautiful. It indicated the merger of two objects that were firmly in the expected mass range for neutron stars, somewhere between 1.1 and 1.6 times the mass of our sun.
So perfectly normal neutron stars.
Textbook. And that initial signal immediately triggered an alert that went out to the world's optical telescopes, giving them a general direction in the sky to start looking.
And what did they see? What was that unique visual fingerprint that confirmed, yes, this is the kilonova the gravity waves told us about?
They saw a rapid eruption of light. It peaked and then faded very, very fast over a matter of days, maybe a week. And most importantly, it glowed this distinct, deep crimson color. Red.
So quick and crimson.
That became the universal signature. If you're looking for a kilonova, that's what you're looking for.
And this is where we get to the really beautiful, complex atomic chemistry. The color itself. The red color of the explosion is the smoking gun. It proves that gold and uranium are being made.
It is. This is the cool part.
So walk us through the mechanism of that deep red glow. Why red?
It's caused by something called the lanthanide curtain. So you have these extremely heavy elements being produced in the blast elements, like the lanthanides, which include europium and, of course, gold, platinum, uranium. They all have these massive, really complex atomic nuclei.
And that means?
That means they have a chaotic, dense arrangement of electron energy levels.
Okay, so there are a lot more places for photons, for light particles to interact with the atom.
Precisely. These elements, which are just churned out in the blast, create this dense, opaque shell around the merger. So when light tries to pass through this cloud of newly minted heavy atoms, those complex electron structures are incredibly efficient at absorbing or blocking high-energy photons.
The blue light, the ultraviolet light.
Exactly. Think of it like a very specific, very thick filter. The blue high-energy light gets immediately trapped or scattered by the chaos of all these heavy elements.
But the red light gets through.
Exactly. The lower energy light, the light at the red and infrared end of the spectrum, is much less susceptible to this. It manages to pass through the dense debris cloud relatively unimpeded. So the light we end up observing is dramatically skewed toward those red wavelengths,
giving the kilonova its signature, rapidly fading red glow.
And GW170817 established that perfectly. Dual detection, rapid light curve, and that telltale crimson color signaling that super heavy elements were being made. That is the classic established signature.
Okay, let's just lay out that standard model one more time.
GW170817 is the classic kilonova. You get the gravitational waves, you get the light, it fades fast. It glows red because of the heavy elements blocking the blue light. That's our perfect confirmed baseline.
That's the blueprint.
What happens when a new event looks exactly like that until the light curve takes a sudden, sharp, and completely unexpected left turn?
And that sudden turn brings us to the dual alert when AT 2025 CVRS enters the scene. Because the initial observations, they mirrored GW170817 almost perfectly. It gave astronomers this massive sense of déjà vu. The countdown began on August 18th, 2025. That's when the gravitational wave trigger S250818K went off.
Yeah, the alert went across the whole global network. The twin LIGO detectors in the US, Virgo in Italy, and the whole international collaboration that includes KJRI in Japan, all of them picked up the signal.
And they immediately sent out an alert.
Immediately.
Right.
To the entire astronomical community, saying, hey, a merger has occurred. And it's important to understand the scale of this. When an alert like this comes in, dozens of observatories, large and small, they drop whatever they are doing, they re-aim their telescopes, and start scanning the sky region provided by the network.
Because the window to catch the light is tiny.
It's just a few days.
But right from the start, the analysis of the gravitational wave data itself, it revealed something crucial that set this alert apart from GW170817. There was an immediate curiosity, maybe even a confusion, about what was actually colliding.
Yes. The signal was clearly a merger, no doubt about that. But the mathematical modeling of the waves indicated that at least one of the colliding objects was unusually tiny. The merger involved objects that were less massive than a typical neutron star.
Specifically, how tiny?
Specifically, the data was consistent with at least one of the components having a mass less than 1 solar mass.
Wait, less massive than our own sun?
Exactly, subsolar mass. This immediately raised a giant red flag, or, maybe a beacon of interest for theorists.
Because that's not supposed to happen.
The standard lower limit for a stable neutron star is around 1.2 solar masses. So to detect a subsolar mass object in a merger, it meant we were potentially seeing something brand new about how stars evolve or how their remnants form.
So even if the signal wasn't super strong?
Right. As one of the LIGO team members noted, even if it wasn't the highest confidence alert ever, the truly intriguing nature of the objects, that subsolar component, that got everyone's attention immediately.
So the gravity wave data gave them a rough map of where to look, which let the optical telescopes follow up incredibly fast.
And that rapid response is just critical for catching these things before they disappear.
And hours later, they found it.
Hours later, the Zwicky Transient Facility, or ZTF, at Palomar Observatory in California, they nailed the location. ZTF is basically designed for this kind of astronomical triage. It scans huge areas of the sky really fast, looking for things that change.
And it found a rapidly fading red object.
A rapidly fading red object, about 1.3 billion light-years away. It was initially tagged with the ZTF name, and then later officially designated AT2025 lots.
Location confirmed, 1.3 billion light-years away. And the initial observations matched the Kilonova blueprint perfectly.
Absolutely did. I mean, this is where the initial belief that this was a standard kilonova really got cemented. About a dozen other telescopes jumped on it. KAG in Hawaii, Wendelstein in Germany, the entire Gruth network of observatories. They all pointed their mirrors at the target.
And they all confirmed the same thing.
They all confirmed it. The light eruption faded fast, and it glowed at those signature red wavelengths.
So if you're an astronomer in those first few days, you're looking at a textbook kilonova. You've got the gravity waves from a merger. You've got the light signature confirming heavy elements being made, glowing red, fading fast.
You're thinking, we've got it. This is the long-awaited second confirmed kilonova, a perfect echo of GW178AIN.
It was textbook.
It was textbook until that initial fading curve bottomed out, and then did something utterly inexplicable for a kilonova.
And this is where the paradox really sets in, the astronomical identity crisis. Because days after that initial blast, the textbook definition was just shattered. AT2025 EOS completely changed its signature.
The initial fast red phase was perfectly consistent with the kilonova, right? But then the event's characteristics just reversed entirely. The kilonova should only fade. That's the physics of it. The radioactive material disperses it and it cools down quickly.
But instead of continuing to fade, AT2025 chills started to brighten again.
It did. And not only did the brightness reverse course, but the light changed color. It decisively turned blue.
So if the red light signals heavy, complex atoms and that lanthanide curtain, blue light signals something completely different.
Completely different. Faster moving material, less obscured, higher energy, which usually means lighter elements.
Yeah, and then the spectrum analysis delivered the biggest shock of all.
The spectra began to show the unmistakable presence of hydrogen. And that is the observation that truly, truly confounded everyone.
It's the ultimate contradiction to the kilonova model.
It is. Neutron star mergers happen after the original stars have stripped off their outer gas envelopes. They're just these extremely dense, neutron-rich objects. A kilonova should not be generating any significant detectable amount of hydrogen.
Because hydrogen is what stars are made of?
Exactly. So the presence of hydrogen, that color shift to blue, and the renewed brightening. All of those are classic, undeniable signs of a core collapse supernova, specifically a stripped envelope type.
So let me get this straight. We have a clear gravitational wave signal that says dead star merger. We have an initial light curve that says kilonova, but then we have a secondary light curve that screams supernova.
That's the paradox. And it created immediate, widespread controversy and deep skepticism in the wider astronomical community.
And that skepticism was rooted in fundamental physics, right?
It was. Supernovae from distant galaxies are generally not expected to generate enough detectable gravitational waves for LIGO and Virgo to pick up. A supernova explosion is, for the most part, symmetric. The waves it produces tend to cancel each other out.
But kilonova mergers are the opposite.
They're highly asymmetric and incredibly violent. They produce a very strong, very measurable gravitational wave signal.
So if the optical signal turned out to be a supernova, the simplest explanation was that the two events were just unrelated. That AT 2025 Fulles was just a typical ho-hum supernova that happened to be in the same part of the sky as the gravitational wave signal.
That's right. And based on the source material, this is precisely where many astronomers just lost interest.
They just wrote it off as a coincidence, a red herring.
They did. They concluded the initial kilonova alert was a bust, that it was unrelated to the later optical brightening. They assumed the gravitational wave alert came from some invisible, dark merger event, and the supernova just happened to be nearby.
But what about the odds of that? I mean, a distant supernova coincidentally appearing in the same gravitational wave map location, that has to be pretty low, right? How did the Caltech team argue against that?
The probability of a chance alignment like that is low, maybe 1 in 100,000, but it's not astronomically impossible. Those gravitational wave mapping boxes are still pretty large areas of the sky. The issue was less about pure probability and more about Occam's razor.
The simplest explanation is usually the correct one.
Right. A merger produces gravitational waves. A supernova produces light. If the light signal later looks unambiguously like a supernova, you just separate the two events.
But the team led by Caltech's Mansi Kasliwal, she's the lead author of the key study, they insisted that something unusual was happening. They refused to just dismiss the connection.
And their perseverance was based on this really deep critical analysis of the data. They noted that the event, it didn't look like an average supernova either. It was an oddball.
How so?
It had the unprecedented speed and the initial red phase of a kilonova, but that was overlaid with the later powerful characteristics of a supernova. They saw that unusual dual-phase light signature as evidence of a connection, not a coincidence.
So the very fact that it didn't fit neatly into either category, not a classic kilonova, not a classic supernova, that's what kept them pursuing it. The messiness of the data itself became the clue.
Exactly. And that critical insight brings us to the hypothesis of the superkilonova. This provides a framework for how one single cosmic event could execute a two-part explosion, producing both that immediate merger signal and the later obscuring supernova signature.
A kilonova spurred on by a supernova.
That's the idea.
And the core argument for this superkilonova hinges on connecting those two extremely strange clues that defy the standard models. The first one, which we touched on, is the nature of the colliding objects themselves.
That's the linchpin. The LIGO-Virgo data showed that at least one object in the merger was less massive than a typical neutron star, a subsolar mass neutron star. And this is the concept of the forbidden mass range. And it's a huge challenge to standard stellar physics.
So why is that mass range, less than 1.2 solar masses considered forbidden or so problematic for a stable neutron star?
Okay, so we have to go back to the fundamental physics of extreme density. When a massive star dies, gravity collapses the core until the matter is so dense that electrons and protons are literally crushed together into neutrons.
And it's the pressure from those neutrons that stops the collapse.
Yes, it's called neutron degeneracy pressure. It's the quantum pressure from these tightly packed neutrons that halts the collapse and stabilizes the star. It's what forms a neutron star.
It's basically the last line of defense against becoming a black hole.
Precisely. And to overcome the outward push of that pressure and stabilize the star, you need a critical amount of mass. And theoretical models, which have been corroborated by decades of observation, place that lower limit, the minimum mass you need, at around 1.2 times the mass of our sun.
And anything smaller than that.
Anything smaller, according to standard models, just can't sustain the neutron star structure. It would either bounce back and never fully collapse, or it would form something far less dense, like a white dwarf.
So if the gravitational wave signature is telling us that at least one of these colliding objects was significantly smaller than 1.2 solar masses, then the way that object was formed must have been fundamentally different from the standard model.
That's the only logical conclusion. And theorists, including Brian Metzger at Columbia, had previously proposed ways for these tiny objects to exist, but they'd never been observed before. They are the essential missing piece of this whole superkilonova theory.
We need a way to explain how the universe created. So Metzger's team proposed two theoretical scenarios for how these subsolar neutron stars could be formed during a supernova. Let's start with the first one, fission. The idea of splitting the core.
Okay, so in the fission scenario, You start with an incredibly massive star that is spinning extremely rapidly as it collapses and goes supernova. That rotation is key.
It's all about the spin.
It's all about the spin. Instead of the core collapsing neatly into one single remnant, the extreme centripetal forces, coupled with the instability of the core, cause the collapsing matter to split, or fission, into two tiny separate subsolar mass neutron stars.
So they're born not as one, but as twins.
As twin, tiny remnants orbiting each other immediately right inside the newly exploding star.
And the second scenario, fragmentation, that sounds like we're building a miniature solar system inside a dying star.
That analogy is actually highly relevant. In the fragmentation scenario, again, you have a rapidly spinning star going supernova. But as the core collapses, the material forms an accretion disk around it.
Like the disk that forms planets around a new star.
Very similar. This disk is highly unstable and lumpy, and that lumpy disk material then fragments and coalesces. It lumps together into a tiny neutron star, much like a planet would form in a protoplanetary disk. Both of these scenarios, fission and fragmentation, they rely critically on that progenitor star spinning really, really fast.
Okay, so the hypothesis goes. We saw the birth and the immediate collision of these forbidden baby neutron stars. Now we can finally lay out the full, elegant superkilonova timeline that reconciles all the data.
Right. The theory is this sequential two-part event, which is why it's hypothesized to be a superkilonova, a kilonova embedded within and spurred by a supernova.
Step 1. A massive, rapidly spinning star explodes in a core collapse supernova. This releases the initial bulk of energy and creates a huge debris cloud full of hydrogen.
Step 2. This massive explosion immediately gives birth to twin baby neutron stars, at least one of which must be subsolar, based on the gravity wave data from S2508 Theron K, and they are born orbiting each other right inside that expanding supernova debris.
Step 3. Because they are born so close together, these newly formed neutron stars quickly spiral in and crash, creating a powerful kilonova merger.
And this is the event that released the strong, detectable gravitational waves and that initial rush of heavy elements.
So now we can use this timeline to explain the contradictory observations. Initially, for the first few days, the light was dominated by the kilonova merger.
Right. That merger churned out heavy, neutron-rich metals, which created that initial, rapidly fading red glow that ZTF and the other telescopes saw. The lanthanide curtain was briefly visible.
But then the main event, that vast debris cloud from the initial larger supernova blast from step 1, it catches up and expands, and that cloud has hydrogen in it. It's still glowing, and it's moving fast.
And that debris cloud expands and eventually obscures the underlying kilonova light. The kilonova is still there, glowing red, but now it's hidden behind the massive supernova ejecta. But that debris cloud itself is energized and glowing, and this is what causes the light curve to later brighten again and turn blue and show those hydrogen spectra.
So the blue color and the hydrogen signature, they're the signature of the larger, faster-moving supernova debris, washing out the underlying red kilonova flash.
That's the theory. The event isn't just a simple merger, it's a merger immediately obscured by its own birth trauma. It's an event that collapses, splits, merges, and then explodes, all within a matter of days.
That is why it looks like a kilonova followed by a supernova.
Exactly. As Metzger put it, the only reliable way theorists can come up with to birth these subsolar neutron stars is during the collapse of a very rapidly spinning star. So if these forbidden stars pair up and merge, the resulting gravitational wave event would be immediately accompanied by a massive obscuring supernova rather than being seen as a bare kilonova like GW1708 Industine. That dual explosion perfectly explains the dual light signature.
It's an incredibly elegant solution to a massive cosmic contradiction.
It is, but it's one that relies on the existence of stars we haven't actually confirmed anywhere else.
Yeah. And this theory is absolutely fascinating, but the research team is also, quick to emphasize the uncertainty here. They stress that this is a tantalizing and interesting theory, but they don't have enough evidence yet to make firm, definitive claims.
And that transparency is just crucial to the scientific process. This is the hypothesis that best fits the messy data, but it all hinges on an unconfirmed stellar remnant, that subsimilar mass neutron star.
But the event is still eye-opening.
Oh, absolutely, because it forces astronomers to expand the models of how massive stars end their lives. The very possibility of neutron stars existing in this subsolar mass range challenges some fundamental assumptions about stellar evolution.
So if this model is correct, was there any part of the data that still didn't quite fit? Even with the superkilonova theory, no theory is perfect.
That's a great point, and the fit is good, But the biggest challenge remains the sheer distance. At 1.3 billion light-years, AT 2012 Kilomeus is much, much farther away than GW 17817 was. That was only about 130 million light-years away.
So the signal is just weaker.
Much weaker. Analyzing the precise mass ratios, the exact chemical composition from that distance, is pushing the absolute limit of our current telescope technology. The fainter details, the subtle differences between a standard supernova and this hypothesized superkilonova ejecta, they're still murky. They really need many more examples to tighten up the parameters.
Okay, so what does this all mean for the future of astronomy? The only way to test this is to find more of them. But now we know that the simple kilonova search criteria, fast, red, and fading, that might be incomplete.
It might be. If the superkilonova model is right, future kilonovae might be easily mistaken for just mundane supernova.
They could be hiding in plain sight.
That's the key takeaway from Caswell and her team. We have to fundamentally change our search criteria. Future kilonova events may not look like GW 70872. They might have this obscure dual signature, and they risk being mistaken for just another run-of-the-mill supernova, especially by automated systems that aren't programmed to look for this kind of dual-phase evolution.
So we need next-generation observational power.
We do. We need something that can catch that rapid initial flash and provide the deep spectral data to analyze the composition changes over time, even for extremely faint, distant events.
So let's detail some of the projects that will be essential for finding these things. These future observatories are designed for exactly this kind of challenge.
Right. We need both massive, wide-field survey telescopes to catch the initial flash and specialized instruments to look at the light that's obscured or at higher energies.
Starting with the Vera Rubin Observatory, this is the project astronomers talk about constantly when it comes to transients. Why is it so vital here?
Vera Rubin is a total game changer because of its sheer speed and its field of view. Its primary mission involves perpetually scanning the entire visible sky every few nights with this massive 3.2 gigapixel camera.
So it'll just catch things faster.
Much faster, much more reliably than even ZTF can now. It will just dramatically increase the probability of catching that crucial early red phase before the supernova component kicks in and washes everything out.
So that addresses the speed challenge. But what about the need to peer through the obscuring debris? The problem that made AT 2025 Elkerets turn blue.
For that, we turn to specific wavelength tools. Caltech is deploying some very specialized ground-based tools for this, specifically the Deep Synoptic Array 2000, or DSA 2000. It's a massive radio telescope array.
And why are radio waves the ideal tool for penetrating that debris cloud?
Radio waves have much longer wavelengths than visible light. They're just much less susceptible to being scattered and absorbed by dense dust and gas clouds, including that huge hydrogen cloud from the initial supernova blast.
So if the theory is correct?
If the theory is correct, the underlying obscured kilonova merger should leave a characteristic radio signature as its own debris cloud expands. And DSA 2000 is designed to capture exactly that signal.
And then, moving beyond Earth's atmosphere, we have space-based assets, like NASA's Nancy Roman Space Telescope. What's its advantage?
Being in space, Roman will offer just unprecedented clarity and resolution. But critically, it has a much wider field of view than Hubble, but with Hubble-like image quality.
So it can see more of the sky with the same precision.
Which is vital for distant events like AT 2025 full planes. It can provide higher resolution light curves and spectra to analyze the chemical changes with way more precision, helping us determine if that late blue light truly is from hydrogen-rich supernova ejecta.
And finally, a focus on the ultraviolet spectrum with NASA's UVX, the Ultraviolet Explorer, which is led by Caltech's Fiona Harrison. Why ultraviolet?
Looking at UV is vital because the initial high-energy component of these explosions often dominates in the ultraviolet. The initial shock breakout, the fastest-moving material, it radiates intensely in the UV band.
So it gives you a look at the earliest moments.
The very earliest moments. If we're dealing with a dual-phase explosion like this, the UV signature might be very distinct and energetic. UVX would be perfectly positioned to capture those first moments before the debris clouds have fully expanded, giving us a clean look at the physics before all the optical confusion starts.
So the path forward is clear. We need more sensitivity, more speed, and a multi-wavelength capability to decode these transient, chaotic, and just dual-natured cosmic events. The universe is forcing us to build better tools because it insists on making things far more complicated than our models allowed.
Indeed. This one event, AT 2025 rolls, have been so eye-opening because it suggests a level of complexity in stellar death we just hadn't mapped out. The possibility of these subsolar mass neutron stars forming inside the collapsing core of a spinning star. It suggests the birth of stellar remnants is a far more chaotic process than we ever assumed.
It fundamentally connects star death and dead star collision
Into a single, terrifying element-forging process, yes.
So the bottom line here is that the universe delivered a potential new cosmic category, the superkilonova, that challenges that classic distinction. And it's all hinged on the detection of an impossibly small subsolar mass object that theorists thought could exist but had never actually seen.
It forces us to reconsider the entire life cycle of the heaviest stars.
Which brings us to the bigger picture.
Right, the relevance to us. If the elements that make up our planet, from the iron in our blood, which is a supernova product, to the gold in our rings, which is a kilonova product, if they're all created in these cataclysmic events, and if we're now discovering that these events can happen in these two-step dual explosions, what other violent, unexpected pathways exist for creating the basic building blocks of life that we haven't even conceived of yet?
A whole new branch of cosmic chemistry.
It could be. The fact that the smallest, most theoretically problematic neutron stars might be born immediately within the largest stellar explosions. It suggests a fundamental and deeply interconnected violence between birth and death in the universe that we are only just beginning to map out. Perhaps the most profound chemical creation requires the fastest, most catastrophic destruction imaginable.